Hello, this is the first in a three-part series of videos to talk about some of the mechanisms of evolution. The two main topics that will be covered in this video are the Hardy-Weinberg principle and the concept of genetic drift. So we'll begin with the Hardy-Weinberg principle because this is the idea that all of genetic drift kind of hinges upon. So we'll be talking about the Hardy-Weinberg principle first. The idea here, for starters, is that the Hardy-Weinberg principle is used to study allele frequencies. What this means is it looks at the number of alleles in a population for a given trait. If you remember back to our chapter on genetics, alleles are characteristics that are passed down from parents to offspring. It's easiest to think about if we're thinking about a classic Mendelian trait, something when there is a distinct dominant and a recessive characteristic. In something more complicated, like a non-Mendelian trait or a polygenic traits, those things won't necessarily follow these patterns quite as well. But for simple traits, this formula is perfect. The formula is actually very simple. P plus Q equals 1. Each letter in this case stands for one of the alleles. So for example, P would stand for, say, the dominant allele, and then Q would stand for the recessive allele. If you add those together and they come out to 1, that means that the formula is in equilibrium, that there's no genetic change happening in the population. The example that your textbook gives has to do with 100 humans, and it's looking at their earlobe attachments. So they either have attached earlobes or unattached earlobes. So in this case, the capital E is going to stand for attached, and lowercase e for unattached. And our lowercase e is unattached. So the next thing to do is to figure out the number of alleles overall. So if we consider just the capital E allele, we've got to figure out how many of these we have. Well, in this case, since there's two capital E alleles in each homozygous dominant individual, that's 80 right there. And then there's 40 individuals that have one capital E and one lowercase e. So that's the 80 from here plus the 40 capital E alleles from our heterozygous individuals equals 120 capital E alleles. If we think about the number of lowercase e alleles, the ones for the unattached earlobes, there's 40 here, again because there's one dominant and one recessive in each. That one's pretty easy to figure out. And there's actually also 40 here, because even though there's only 20 individuals, each of those individuals has two lowercase e alleles, since they're homozygous recessive. So lowercase e in this case is going to equal 80 alleles for us, which makes sense because we have 100 total individuals. Each individual has two alleles, so these two numbers have to add up to 200, which in this case they do. So we know that we figured that out correctly. The next thing is to figure out the allele frequency. This is actually relatively easy. You just take the number that you figured out for each allele and you divide it by the total number of alleles available. So in this case, we're dividing both of these numbers by 200, which is going to give us an allele frequency for capital E of 0.6, and then an allele frequency for lowercase e of 0.4. It's not picking up my pen. There we go. So if we punch these two back into our formula, because remember I said to you up here that P would stand for the frequency of capital E and Q would stand for the frequency of lowercase e, 0.6 plus 0.4 does give us 1. So in that case, this population is at equilibrium. Another way to figure that out is to use this expanded formula. This is usually used if the population is not at equilibrium. You can kind of figure out which characteristics are representing that. If we think about why the heck we're using this, P squared, remember P stands for capital E. So P squared represents our homozygous dominant individual. 2PQ represents our heterozygous individuals, where there's one of each allele. And then Q squared represents our homozygous recessive individuals. So all we have to do is take these numbers and put them into the equation. So if we take 0.6 and square it, you're basically just multiplying 0.6 by 0.6, so we end up with 0.36 for that one. Then we're adding that with 2pq. So if we multiply 2 times our p-value, remember our p-value is 0.6, so that would give us 0.12. Then that would be times 0.4, which would give us 0.28. Then we're adding that together with q squared. Again, remember, q is represented by lowercase e, which is 0.4, which comes out to 0.16. So if you add those together, those end up again coming out to 1, which supports for us that this population is in equilibrium. Remember, this doesn't always have to come out to 1. What that will tell us, though, is if this comes out and the answer does not equal 1, then we know the population is not in equilibrium, and it's changing due to some factor. The reason we add all this stuff up is one of these factors is going to be out of balance, and you can kind of take the time to figure out which allele is then the one that's becoming more common in the population. So in examples where you add this up, don't freak out if it doesn't add up to 1 at the end. That's not a big deal. That just means that the population is changing, that there's some kind of force that is causing it to move away from one allele and towards another. So we'll talk about some things as we finish up this video that would cause the population to no longer be at equilibrium. The two factors that would cause the population, or that I should say could cause the population to change, are both examples of what we call genetic drift. Genetic drift is defined as any change in the allelic frequency of a population. So those alleles we were just looking at in the Hardy-Weinberg formula, if there's a change in those alleles, it's no longer at equilibrium, right? That number will not add up to 1, and so then genetic drift would be taking place. The two most common examples of genetic drift are the founder effect and genetic bottlenecking. Something to keep in mind when it comes to any kind of genetic drift is that this is going to happen more frequently if the population is small. If you remember that coin flipping example we did way back in the chapter on Mendelian genetics, the whole purpose of that coin flip lab was to show you the power of probability. We all know that when you flip a coin, there's a 50-50 chance of getting either heads or tails. If you flip a coin, say 3 times though, you could very realistically get heads all 3 times. In that case, it doesn't look like the odds are 50-50 at all. It looks like the odds are 100% in favor of heads, even though we know that isn't true. So a way that you could make it a lot closer to 50% is instead of flipping the coin 3 times, maybe you flip the coin 300 times. Over the course of those 300 coin flips, probability should average those numbers out where they're going to come a lot closer to 50%. So it works kind of the same way with genetic drift. Genetic drift should all average out. Like differences in the alleles in a population should come out to average pretty much equilibrium. That idea of you add them all up and they come up to 1. The problem is if your population is really small or your population size is changing for some reason, that's when genetic drift can happen. The easier of these two concepts to look at is called the founder effect. The idea behind the founder effect is you have a few individuals from a population that are starting a new population that's isolated from the original. So in this case, we have these little ladybugs. Some of them are red and some of them are yellow. The idea is some of them get blown off of the mainland where they're occurring, and then they get to an island when there's only red individuals. So maybe just by chance, a handful of these red individuals were blown off the island in a storm. Blown off the mainland in a storm. They wind up on an island where they begin reproducing. Since none of the yellow individuals were removed, then we end up with all red ones in the population. So this idea is called the founder effect because you have a few small individuals that found a new population. And as the founders of that group, they only present the genetics that they have. So there's a chance that you could end up with some restricted genetics in those populations. The other concept is called genetic bottlenecking. We'll look at a graph of this first, and then after that, we'll take a look at this image. What this shows you is the population. So the population for our group is going strong. There's some kind of bottleneck event, something that affects the population negatively, and it drops off very, very quickly. So now our population is extremely low. There's 2 places for it to go from here. They could slide off into extinction, or maybe conditions change or the population adapts and they rebound eventually close to their point of the original population. What we're seeing though when this happens is as this part drops off, as a lot of these individuals are dying off, that's limiting the genetics of the population. So once that population does rebound, this has the effect that we call a genetic bottleneck. It artificially restricts the amount of genetics in the population. Another way of looking at this is with this typical bottle example, where you have your original population. All of those colors represent the wide variety of traits in that original population. If for some reason the population numbers drop off catastrophically, right? It says some kind of catastrophic reduction in population takes place, and you're only left with a few chance survivors. In this case, they all have just the blue and the yellow traits, whatever those colors represent. You could fill it in with almost anything. Our new population then only has those characteristics, only the blue and yellow ones, because all of the other individuals have been removed from that population group. As we've mentioned a couple times already, this example happened to the human population around the time of the last ice age. It's estimated that the human population was reduced to about 1,000 individuals. So we're actually the result of a genetic bottleneck. Everybody on the planet today is the result of one of those 1,000 individuals. We could trace our lineage back to those people that were left at that point. So I appreciate you guys taking the time to watch. Hopefully this helps with the Hardy-Weinberg equilibrium principle, as well as some of the things that could cause that number to not equal 1. So remember, when that one comes out to 1, it's in equilibrium. When it doesn't come out to 1, then there's some kind of an unbalanced factor going on in the environment. Thank you for watching, and make sure to answer the questions after you're finished.